Proportionality constants in nature are fundamental numbers that link related physical quantities such as the gravitational constant, which connects the force of gravity to the masses and the distance between the two objects, or Planck's constant that relates the energy of a photon or of a light wave to its frequency. These constants are crucial for expressing the laws of physics as precise mathematical relationships. In this video, we're going to have a closer look at the most common proportionality constants, and in particular, we're going to look at the units for these constants to give us a better idea of how they are defined and why they work. So let's start with the gravitational constant. Let's say we have two objects, two gravitational objects with that are separated by some distance d. Now we write the proportionality equation as, and this is a force equation, that force is, let's call this m1 and m2 for mass 1 and mass 2. So force is proportional to mass 1 times mass 2 divided by the distance squared times some proportionality constant, which needs to be defined. It needs to be calibrated, actually. So this constant relates these parameters, these variables, to a particular unit system. So basically the point of a proportionality constant is to relate the variables to the unit system. Okay, so currently we use the MKS system, but if we used, which is the standard SI standard, but if we use the CGS system, this numerical value would be different. Okay, the numerical value of the constant would be different. The proportionality, of course, will be the same. So once this constant is calibrated to the current standard, we can write something a little more precise. We can write force is equal to m1 times m2 divided by the distance squared times the gravitational constant. Okay, so now we can write, now that we've calibrated to the MKS system, we can actually write a constant, the value of the constant. Okay, so this relationship holds true in the MKS system if the gravitational constant is calibrated to the MKS system. Okay, so let's do some unit analysis. So what I'm going to do is I'm going to write down the units for the variable. Okay, the mass in this equation is variable and the distance between the objects is variable. Okay, so this is a variable. So the units for the variable are kilogram squared divided by the meter squared. Okay, so those are the units for the first part of the equation. And now what we're going to do is we're going to write the units for the gravitational constant. We'll put it beside right here. So because this is a proportionality constant, what we need to do for the units of, to determine the units of g, is first we need to invert this. So we need to invert the units for the variable. So I'm going to write meters squared over kilogram squared. And then we know that the force, the units for this equation have to end up being the Newton. So then we just write the Newton here. And then the final units are going to be just the Newton. And notice that I'm always putting my units in square brackets like I always do to distinguish between the unit section of an equation and the actual equation itself. Okay, so this is how proportionality constants work. You've got in the equation, usually you have a variable, you have a constant, Okay, you write down the units for the variable, you invert them, so you make it reciprocal, you invert them, and then you write the units that you want. At the end, this cancels this cancels this, right? This cancels this cancels this, and you end up with the units of the Newton. So this is a nice way to remember the units of the gravitational constant by writing them like this. And of course, you can reduce these constants if you want to maybe extract more information or more intuition about the true meaning behind the gravitational constant. But for the most part, it is a proportionality constant, where the proportionality is between, in this case, the masses and the distance between the two masses. So now we're going to do the same thing for the Coulomb constant, for the law of electrostatics. So what we have a proportionality. So force is proportional to, and now we've got two charges separated by a distance, d. Okay, so we have q and q. So the formula is very similar to the gravitational formula, where we have, instead of m1 and m2, we have q1 and q2 divided by the distance squared, okay, times some proportionality constant, which needs to be calibrated. So this needs to be calibrated to the MKS system. Okay, so once it's calibrated, we can write force is equal to Q1, Q2 divided by the, divided by the distance squared times the Coulomb constant, which is often written like this. Okay, so now we're going to write the units for the variable. So the units for the variable, so the unit of charge is the Coulomb. So the units for the variable are going to be Coulomb squared divided by meter squared. Okay, and now we're going to do the same thing we did with the gravitational constant. We're going to write the constant for the Coulomb. For the Coulomb constant, we're going to write the units as, so we're going to invert this. We're going to invert that. So we're going to write meters squared divided by Coulomb squared, and then we're going to write the Newton. So these are the units for the Coulomb constant, and this cancels this cancels that, and the final units are what we want, which are the units of force, or the Newton. Okay, so this reciprocal method can be done, applied to all of the proportionality constants. So this is an easy way to figure out the units of the Coulomb constant. If you can't remember them for some reason, if you didn't memorize them, then this is an easy way of writing the units for the Coulomb constant. So next we're going to apply the same procedure to the to Planck's constant. Okay, so now this is an energy equation, so the proportionality is going to be in terms of energy. So energy is proportional to the frequency of light. Okay, well, I'm not going to say photon, I'm just going to say light. I'm going to call it a light wave. Energy is proportional to the frequency of a light wave times some proportionality constant, which needs to be calibrated. Okay, so we're talking about a light wave that has a frequency where the wavelength is, from peak to peak. Okay, the wavelength is from peak to peak. And so this is what we're talking about. And so once K is calibrated, we can write an exact equation where we have energy is equal to frequency times Planck's constant. Okay, so what we're going to do here is we're going to write the units of frequency, and this is where I need to apply modified unit analysis, and I'll explain why. Okay, so historically, frequency is written as 1 over s. Okay, and so 1 over s is per second. So just for a minute here, I want to talk about per second. So the units of per second are 1 over s. Okay, or you could write s to the minus 1, which is often done. Okay, and so, but also the units of frequency, they're written as 1 over s. Okay, so the reason I have a problem with this is because let's look at something like acceleration. So the units of acceleration are meters per second squared. Okay, or you could write them as meters times second to the minus 1. Okay, or you could write them as meter per second per second. Okay, these are all equivalent ways of writing the units for acceleration mathematically. Okay, so the problem I have with frequency as being written as per second is now we can't distinguish between the per second, let's say, in the units for acceleration, because this is not cycles per second, it's meters per second squared. So this per second is not the same as this per second. Okay, this frequency is literally cycles per second, and you know in modified unit analysis I use the delta symbol, the triangle, for the unit of the cycle. And so this is why I think it's important to use a symbol for the domain of frequency, for the domain of the cycle. I think it's very important to do that, and so I write the units for frequency as cycles per second. Okay, so now to get the proportionality constant, to get the units for the proportionality constant, we have to take the inverse of this, of the variable. The variable is frequency. So I'm going to write second per cycle. Okay, and then we write the unit for the joule here. Okay, so then this cancels this cancels this, and we end up with the units of the joule. So just looking at Planck's constant as a proportionality constant, which it is, we can see that these units, the units of second per cycle, are in the units of Planck's constant. So Planck's constant, the units of Planck's constant is usually joule times second, which you can see right here, joule times second. Okay, but there's something missing from the units of Planck's constant that is very, very important in my opinion, and that is the second per cycle. And the second per cycle, okay, the units second per cycle are the units of the wave period. Okay, so the units of Planck's constant literally translates to, you can read it like a book, translates to the energy of, okay, times and of are the same. So joule times second per cycle is literally translates to the energy of one wave period. And this interpretation is quite a bit different than the standard interpretation, and that's because we handicapped ourselves by making the units of frequency 1 over s per second, or s to the minus 1, instead of cycles per second. So I think this is a really important point. Looking at Planck's constant from the perspective of a proportionality constant makes it very clear that we need to have a unit, a symbol for the unit of the cycle, and then you get what I believe to be a better interpretation of the units of Planck's constant as the energy of one wave period. Okay, so hopefully that makes sense, and this is the main reason actually that I wanted to make this video, was to make this particular point. Okay, and so for the sake of completeness, we are going to look at the famous E equals mc squared equation. We're going to apply the same procedure to this equation and see whether we can find a proportionality constant see what the proportionality constant is for this equation. Okay, so we've got the proportionality is that energy is proportional to mass times some constant, which needs to be calibrated for the MKS system. Okay. So once this is calibrated, then we can write E is equal to mass times the proportionality constant, which actually happens to be c squared. So c squared is a constant, and it is the proportionality constant between mass and energy. So we're going to write the units for this equation. Okay, we're going to start by writing the unit of the variable, which is the mass. So the unit of mass is kilogram. Okay, but to apply the proportionality procedure that I'm implementing in this video, I'm going to write this as kilogram over 1. Okay, so these are the units, and you'll see why I'm doing this in a minute. So these are the units of the variable, and now we're going to write the units of the constant. So in order to write the units of the constant, we need to reverse this. We need to write the reciprocal of this. So I'm going to write 1 over kilogram. Okay, so we reverse the units of the variable, and then we just write joule here. Okay, so these kilogram. So these are the units of c squared. Okay, and so what I'm going to do is, instead of writing the units of joule like this, kilogram, I'm going to write the units of joule as kilogram meters squared per second squared, right? And you will see that these cancel, the ones also cancel, and you end up with the units for c squared are meters squared per second squared, which is correct, right? So you can apply the same proportionality constant procedure to even equals mc squared, and you can see that c squared is really a proportionality constant in this equation. Okay, so that's all I'm going to do for today. As I said before, the main reason I made this video was to give further evidence that the units for frequency should not be 1 over s, okay, should not be per second, but the domain of the cycle needs to have its own unit. And in modified unit analysis, that symbol I use is the delta symbol. And so the units for frequency are cycles per second and not per second. Okay, so that is all I'm going to do for today, and I hope everyone is doing great, and I'll be back.